We started section 3.4 last lecture on the chain rule, and this rule tells us how to take the derivative of composite functions. And we did a couple of examples, but we're going to do a lot more practice with the chain rule now and finish this section. This is a copy of the chain rule that we saw last time. I just wanted to review the rule before we started doing examples. So we're dealing here with a composite function. So our function capital F is f composed with g, little f composed with little g, which of course is defined to be f evaluated at g of x. So we identified that we have what we call an inner function and an outer function. So we can see here g of x is the inner function, and then capital F would be the, or sorry, lowercase f would be the outer function. And so we derived this rule that to find the derivative of capital F, which is the composition of these two functions, you multiply the two derivatives, f prime times g prime. But when you compute f prime, it's not f prime of x, it's f prime evaluated at the inner function. And we also saw this in the Leibniz notation. dy dx represents capital F prime. dy du represents the first term here, and du dx the second term. And the easiest way to think about this is we have our dy dx here, we keep them here on the right, and then it looks like we've multiplied and divided by du. So two notations for the same rule. Sometimes it's easier to think about one versus the other, depending on the situation. I'm going to do a couple of examples here. First, I'm going to do this first one just like we did last time, writing out all the details, and then I'll show you a way you can start thinking about this without having to write out as much and make the work go a lot faster. So first of all, you need to identify that the function here is a composite function, and that's because the simple function would just be sine of x, but we've got something else where we would normally just have x. That means there's an inner function plugged into an outer function. So the first thing we did was identify the inner and outer functions. So here, the inner function we've been calling u, and that would be pi x over 4. And then the outer function, I'll just say y equals, and notice if you plug the u into the formula, you would have sine of u. So then, using the chain rule, we know we're going to need both of these derivatives. So from the top formula, u is written as a function of x. So when we compute the derivative, it would be notated du over dx. And basically we have a constant times x, right, where the constant is pi over 4. And we've seen this before, that the derivative of a constant times x is just the constant, because the derivative of x is 1. So we get pi over 4 for that derivative. And then from the second formula, you can see y is given as a function of u. So the derivative would be notated dy over du. And we know the derivative of sine is cosine, so this would be cosine of u. Now the chain rule, we're trying to find dy dx, which is in the prime notation, that would be capital F prime, which is in here in Leibniz notation dy dx, right, because we're viewing y as being the same as capital F, and f is a function of x, so it needs to be over dx. Now the chain rule says, right, the easy way to remember it, keep the dy, keep the dx, and then multiply and divide by du. Now those are the two derivatives we just computed on the top right, so we can just substitute in. dy du is cosine of u, and then du dx is pi over 4. And then we need to back substitute. I'm going to put the pi over 4 in front, and then I have cosine of u, but I need to plug in for u. If you look up at the definition, up at the top, we said u is pi x over 4. And now we have the derivative we're looking for. So that's writing out everything in full. Now I want to start introducing how you can think about this without having to write so much. So you start out the same. You recognize this is a composite function. So first think about the outer is clearly the sine function, right? The inner is what's in the parentheses, the outer is sine. So we know we're going to need the derivative of the outer function times the derivative of the inner function. So if this were just sine x, the derivative would be cosine of x. So we would start by saying cosine of, and instead of x you have to keep the inside part. So you would write cosine of pi x over 4. Then you know you're not done because you also have to multiply by the derivative of the inner function. So go ahead and look at that and compute that derivative. So we did that before, right? Derivative of this inner part is just pi over 4. So then you multiply what you had already by that extra factor, pi over 4. So that's the derivative. The pi over 4 is the derivative of the inside part, is how we often refer to that. So if you use that thought process, you don't have to write any of this other stuff, right? You could go straight to here by thinking about it that way. Okay, let's do the second one. Let's see if we can do this one using the shorter method. So first of all, let's make sure we get the correct notation. So here w is given as a function of t, so that means the derivative notation would be dw dt. Now we have a constant times a function, and we've already seen the rule that says you can just carry along that constant. Now we have cosine of t squared, so we recognize that again as being a composite function because it's not just plain cosine t, it's cosine of something else. So we start with recognizing the outer function is cosine, and we know we need the derivative of the outer function. So we know the derivative of cosine is negative sine. So we have negative sine, but you have to keep the input the same, right? So it's not negative sine t, it's negative sine of t squared. Now we need to have the extra factor of the chain rule multiply by the derivative of the inside part. The inside part is t squared, so the derivative of t squared is 2t. So just to make a note where that 2t came from, that's the derivative with respect to t of t squared. And that's it. That we could do one more step to simplify this. The 3 times 2 is 6, and then there's a negative sign, so negative 6, and it looks better to pull that t out in front. And then we have the sine t squared factor. Okay, so we got to our result with a lot less writing than if we had defined the inner and outer function and written all that out and computed the derivatives, right? So you'd get the same result, of course, but this is just a faster way to think about it. Here's some more examples of finding derivatives. So looking at this first function, the big picture is we have a product. Within that, we have a composite function, right? This e to the, instead of x, we have something in place of x. That means that that exponential part is a composite function. But that composite function is multiplied by x to the 4th. So the bigger picture is we have a product. So you actually have to start with the product rule before you use the chain rule. Okay, so the product rule for f prime will have first times derivative of the second. I'm not going to compute it yet. I'm just going to write here that I need to compute it. Plus second times derivative of the first. So in the next step, we need to calculate these two derivatives. So keep the x to the 4th. Now here, this next derivative is notice it's a composite function. So we need to use the chain rule on this derivative. Okay, so let's go through the chain rule. The inside part is what's in the exponent, 3x minus 1, which means the outer function is just the exponential function, e to the x. Now we know the derivative of e to the x is itself. So you start by just writing itself. And remember, you keep the inside part. It's not e to the x, it's e to whatever's there. But then there's an extra factor, and that's the derivative of the inside part. So we need the derivative of 3x minus 1. And that's an easy derivative, right? It's 3 minus 0, which is just 3. So I'm going to put that in front. Okay, so again, just where this came from, we're taking the derivative of this composite function. We said the outer function was the exponential, e to a power. If it were just e to the x, the derivative would be itself. So we use that, we write itself, but you always keep the inner part there. You don't revert back to a simple x. And then the second factor is the derivative of the inside part. So the derivative of 3x minus 1 is 3 minus 0, which is 3. So we multiply by 3. Okay, so that completes to this point. Then we have plus this exponential term times this other derivative, and that's a simple power rule, so 4x cubed. So then we could make this look a little bit nicer. The first one we could write as 3x to the 4th times e to the 3x minus 1, and then plus 4x cubed times e to the 3x minus 1. Okay, that finishes the first one. Number 2, the big picture is we have a quotient, right? But within that, we have a composite function. This numerator, instead of the plain square root of x, it's square root of something more complicated. So the numerator is a composite function, but it's just a part of this quotient. So we actually have to start with the quotient rule before we use the chain rule. Okay, so start with our notation for the derivative. We could just say g prime of x equals, now the result's a quotient. The new denominator is the original denominator squared. Now in the numerator, we start with bottom as it is, times derivative of the top. I'm not going to take it yet, I'm just going to put d dx. Now I'm going to put the top, but I know because there's a square root, right? We've seen this before. It's going to be easier to write that as a 1/2 power. So that would be x cubed plus 1 to the 1/2. So that's bottom times derivative of the top. Then we have minus top, I'll just leave it as it is with the square root, times derivative of the bottom. Now we need, in our next step, we need to compute the two derivatives that are in there. Okay, so we'll keep our denominator the same. Okay, then we keep, in the numerator, keep the first factor. Now let's compute this derivative. So this is a composite function, right? Remember the 1/2 is a square root. So we have a square root and then something more complicated than just x inside. So let's identify the inside and outside parts. The inside is what was under the square root, right? The x cubed plus 1 is the inside part. So that means the outer function is the square root function, which is the same as the x to the 1/2. So if the outer function is x to the 1/2, how would you compute its derivative? Well, that's a power function. So use the power rule, which says you bring the power down in front and reduce the power by 1. Okay, so when you bring the 1/2 down in front, we have this 1/2. Now you keep the inner part the same. So the part in parentheses stays the same. Now we reduce the power by 1. The old power was 1/2. When you subtract 1 from that, we get negative 1/2. But we're not done with the chain rule, right? That's the derivative of the outer function. Now we multiply by the derivative of the inside part. So the derivative of x cubed plus 1 would be 3x squared plus 0. So it's just 3x squared. Okay, so that was the work to get this derivative. So now we need to keep going in our numerator, so copy this next part. And now multiply that by this other derivative, which we can easily calculate. Derivative of 2x minus 3 is 2 minus 0, which is just 2. And then let's just do one step of simplification here. These are often pretty messy, and it's a lot of work to simplify some of these sometimes. So on the first term in the numerator, I'm going to move this to the front and maybe put it over the 2. So we'd have 3x squared over 2 times this factor times this factor. Now that has a negative exponent, so you could put it in the denominator, but we can't move it down here because there's another factor over here that would affect that. So one option is to make a new fraction in the numerator. So we have our 3x squared over 2. We also have that factor 2x minus 3. And the only thing left is that factor to the negative 1/2. So we could pull that down to this denominator, and then it would become a positive 1/2, which is a square root of x cubed plus 1. So that takes care of all the terms in this part. Now we have minus this other term, and that one's pretty easy to deal with. I'll just put the 2 in front. So I think I would stop here with simplification. There's lots of other things you could do, but I'm not expecting you to do huge amounts of simplification on these on your quizzes or tests. Main thing is to be able to apply, in this case, the quotient rule, and at least get to the point where you've taken all the derivatives. From there, I would count this right? You don't have to simplify. Okay, so hopefully you're getting a better feel now for how to work with these problems, and you're seeing we're combining lots of rules, right? On number 1, we combined the product rule with the chain rule, but we also used the power rule. Down here, we used the quotient rule along with the chain rule, and some other rules as we went through, right? Another thing is, at some point you can skip this step where you write d dx of something. So when you're using, like this one, we use the product rule. We did first times derivative of the second. So I wrote here the first, and then I wrote out derivative of the second. Once you get comfortable enough with these, you don't need to write derivative of the second. You can just go ahead and compute it and write it. Same thing over here, plus second times derivative of the first. You don't need to write this eventually. You can just go straight to calculating that derivative in your head and going here. So if you do that, you would skip this entire line here, and you would just go straight to this. Same with the quotient rule. I wrote out bottom times derivative of the top, minus top times derivative of the bottom. You could skip that and just go ahead and compute those derivatives and put them in. You could leave out this entire step. Some more examples. So in the first one, we've got t to the 5th times the cube root of some expression. Right, so the big picture is, this is product. So we need to use the product rule first. Then we'll have to use some other rules within that. Our notation here, since y is a function of t, the derivative would be dy dt. Now start with the product rule. So first is t to the fifth. Now I told you could skip this step, but I'm going to go ahead and write it for people who it still may help at this point, right? So now derivative, and my independent variable is t, so I would write d dt of the second. Now the second is a cube root. So just like with square root, which we rewrote as a 1/2 power, with cube root, it's going to help to write that as a 1/3 power for taking the derivative. So we take what's inside, t squared plus 9t, and put that to the 1/3 power. So that's the derivative of the inside part. Continuing with the product rule, we have plus the second, so I'll just copy it as it is, times derivative of the first. Now we still need to calculate those derivatives. So we keep this t to the fifth. Now the second term is a composite function, right? Because if this were just t to the 1/3, that would be a power function, and we know how to take its derivative. But we have something in place of t. That's the inside part. Okay, so we just identified the inside part as what's in the parentheses. So the outer function is like t to the 1/3. If we just had a t here, right, that would tells you what the outer function is, t to the 1/3. And we recognize that again as being a power function, so we use the power rule. You bring the 1/3 down in front, reduce the power by 1. Okay, so let's do that. We bring down the 1/3. Keep the inside part, and then reduce the power by 1. So the new power is going to be 1/3 minus 1. Right, so if you get a common denominator of 3, that comes out to negative 2/3. That's the new power. Now we're not done, right? That was the derivative of the outer function. Now we have to multiply by the derivative of the inside part. The inside part here is what's in the parentheses, t squared plus 9t. So we need the derivative of that, which would be 2t plus 9. Okay, so we just completed this derivative using the chain rule. We're ready to move on. So now plus, copy that part. And then we have another derivative here, but this is an easy one. Using the power rule, we get 5t to the 4th. Okay, and you could simplify that, but I'm not going to do that. Let's go on to the second one. We have this composite function, right? We've got tangent with something plugged in place of plain x. But that's just part of a quotient. So you have to start with the quotient rule on this one. Okay, so here z is a function of x, so that means the derivative would be written dz dx, or you could just write z prime. And we're using the quotient rule, so we start with the denominator is the easiest. Take the original denominator and square it. Now in the numerator we take bottom times derivative of the top. This time x is my independent variable, so I write d dx of the top. Then we have minus top times derivative of the bottom. Now let's compute those derivatives. So our denominator, first of all, we multiply exponents, so that's x to the 6th. Now in the numerator, we keep this x cubed. Now here's this next derivative is where we need to use the chain rule. So we've got tangent of something other than just plain x, right? We discussed this earlier. So the part inside tangent, in the parentheses, that's 8x plus 7 is the inner function, and the outer function is the tangent function. So first we need to remember the derivative of the tangent function. Right? We learned that a while back. The derivative of tangent is secant squared. Okay, so we're going to write secant squared, but it's not of x, it's of the inside part. Now that's only half of the chain rule, that's the derivative of the outer function. Now we need to multiply by the derivative of the inside part. So the derivative of 8x plus 7 is 8. So we need to multiply by 8. Now if you write it here, it could be confusing. It might look like it's inside the secant squared function. So it's actually better if you just write it out in front. Okay, so we just computed this derivative using the chain rule. Now we move on. The rest of it's easier. So we copy the next part. And then this last derivative is just a power rule. Again, if you write it at the end, it might look like it's inside the tangent. So it's probably better to put it in front, but I didn't leave space, so let me erase that. Okay, now I'm going to put my tangent over here. And now the derivative of x cubed is 3x squared, so put that in front. Okay, and there's a little simplification you can do, but I think we'll just stop here. The rest you already know how to simplify. Now we're going to think again about exponential functions and finding their derivatives. In an earlier section, we learned the derivative of e to the x is equal to e to the x. And we started talking about other exponential functions, such as 2 to the x, 3 to the x, and so on. And we got part way through finding their derivatives, but we didn't complete it. Now that we know the chain rule, we can use that to find the formula for the derivative of any base b to the x. It doesn't have to be e to the x, it could be any number. So we can see the formula here, but we want to derive that. So we're going to rewrite b to the x using a property of exponents. So we know that b can be written as e to the natural log of b, right? From pre-calculus, e and natural log would cancel, and that's the same. This right side is the same as b. So now we want to rewrite b to the x by replacing this b with e to the natural log b. And so we've written it like this. So now, to find the derivative of b to the x, first we replace b to the x with this formula we wrote here. Now, natural log of b is just a constant, because b is a constant. And so we have e to a constant times x. This is a composite function, where the inside part, instead of just having an x here, we have something else. So this exponent is the inside part. The outer function is the exponential function e to a power. So we know the derivative of e to the x is itself. So using the chain rule, we start with itself. Now the other factor of the chain rule is the derivative of the inside part. So again, the inside part is this exponent. Next step, we want to compute this derivative. So we keep this part out in front. Now this natural log b, remember, is a constant. So this is a constant times x, so its derivative would just be whatever this constant is, which is natural log b. Now the next step is to simplify this first factor. Again, e and natural log cancel. So this is just b, but it's still raised to the power x. So we rewrite this as b to the x. Right, we did that same thing right up here. And then still multiplied by natural log b. So this is our result for the derivative of b to the x. And so here's summarizing the formula. We now have a formula for the derivative of any exponential function of the form constant b raised to the power x. So think about just a quick simple examples while we're here. The derivative of 2 to the x. So using that formula, the first thing, derivative of b to the x is itself times this other factor, natural log of b, where b is the base. So over here, derivative of 2 to the x is itself times natural log of the base. What about derivative of 10 to the x? Derivative would be itself times natural log of the base, which in this case is 10. What if you wanted derivative of e to the x? Now we already know this one is e to the x, but what if we used this rule instead of the rule we already know? This would say the derivative is itself times natural log of the base. Now the base here is e, but then we all have seen before natural log of e is equal to 1. And so when you simplify this, it's just e to the x times 1, which is e to the x. So we get the same result that we already knew by using this rule. Here's another example of computing some derivatives. So in this first function, you can see the big picture is we have a quotient. So we're going to, you could use the quotient rule. And that would be perfectly fine. But this is one of those cases where you can get out of having to use the quotient rule by rewriting the function using a negative exponent. So we're first going to rewrite this function as h of x equals 3 to the negative x power. And this is an exponential function, right? It's not a power function. Because power function, you'd have the x would have to be in the base and the power would be constant. Because the x is in the exponent, this is an exponential function, but it's not just a plain 3 to the x, it's 3 to some other expression. So we're going to have to use the chain rule to handle this one. Okay, so using the chain rule, we need to think about what is our inner and outer parts. So the inner part is the exponent, negative x. That's the part that's replacing where we would like to have just a plain x. So that means the outer function is the exponential function, 3 to a single letter. Right, we could call it u, 3 to the u. So with the chain rule, to find our derivative, we start with the outer function, 3 to the x. What is the derivative of 3 to the x? Well, it would be itself times natural log of 3. So itself here is actually 3 to the negative x, right? You have to keep that inner part the same. Then we multiply by natural log 3. That's the derivative of the outer part. Now look at the inner part. Well, that's negative x. We need to multiply by the derivative of negative x, which is just negative 1. And then we could simplify this. We could keep our negative sign out in front. The natural log 3 is a constant. It's in the numerator. And then if you wanted, instead of writing 3 to the negative x, you could put it in the denominator as 3 to the x. Okay, so there's h prime. Now the second one, this is another exponential function because the variable is in the exponent. This is very similar to what we just did. It's not a plain 2 to the x, it's 2 to the something else. So we're going to have to use the chain rule again here. Okay, so our derivative So again, the inner part is the exponent, 1 minus 4x. The outer part, outer function, is the exponential, 2 to the u. So we start with the derivative of the outer part. Derivative of 2 to the u is itself. So here we just write itself. And then we multiply by natural log of the base, which in this case is 2. That's the derivative of the outer function. Now we multiply by the derivative of the inner function, 1 minus 4x. That derivative is negative 4. And then just to make this look a little nicer, I'll put negative 4 first, natural log 2 second, and then the exponential part. We should probably add some parentheses, otherwise you might think it's natural log of 22, right? So maybe putting them here would work, right? Okay, so that finishes our section on the chain rule. And we'll see that we use this rule a lot when we're computing derivatives because these composite functions are very common. So we're continuing in chapter 3 where we've been learning differentiation rules. So all of these rules apply to functions that are written in the standard function form, f of x equals and then some expression in terms of x. So remember, f of x is y. So they're all in the form y equals some expression with x's in it. In this section, we're going to consider functions that aren't given in that standard form. And we'll learn that even if they're not in that form, we can find a way to calculate the derivative of functions like that. As I was just saying, the functions we've been working with so far all can be expressed in this form, where it's y equals some expression with x's in it. Right? Both of these equations have that form, and sometimes we call the y the function name f of x or h of x or whatever. So all the rules we've been learning for taking derivatives are based on having your function written in this form. We call this explicit form. These are explicitly solved for y. Now looking at the bottom, we have some other equations that are not solved for y. Right? They have x and y in it, just like the two up here. Right? They still have it's still equations with two variables, but it's not in that explicit form. So these are called implicit functions, or they're defined implicitly. So we'll consider in some cases you can solve these for y just by using algebra and put it in explicit form. Like this first one we'll work on the next slide. It's pretty simple to solve that for y. The second one's a little more challenging to solve for y because notice there's a y cubed here and then there's another y in this other term. That makes it a lot harder to solve for y. So in cases where we can solve it for y, we could do that, and then we could apply our derivative formulas if we wanted to find dy dx. But what about cases where we can't solve for y? We'd still like a way to find dy dx because that's related to the slope of tangent and other interpretations. Now we're going to consider this equation we just saw on the previous slide, x squared plus y squared equals 25. We've already said that's an implicit equation. It defines y implicitly as a function of x. So if we tried to solve this for y, we would start by subtracting x squared from both sides and then take the square root of both sides. Right, so the right side looks like this. Notice you'd have to put plus minus because you took the square root of both sides. And the left side at that point would just be y. So now it's in explicit form, right? So here it was given to us in implicit form, and we were able to rewrite it in explicit form. So we can consider the graphs too. And actually, before we consider the graphs, notice because of the plus or minus, there's actually two separate explicit equations that correspond to this one implicit equation. So now let's think about the graph. So the original graph, you probably recognize this as the equation of the circle with centered at the origin and radius 5, square root of 25 is the radius. So here in red, that's the graph of the given implicit equation. And notice that this fails the vertical line test, which means it's not a function. So in this case, y is technically not a function of x. Now look at the two functions we got in explicit form. If you take the version with the plus, that means the y values are always positive, so it's only going to give us the top half of this circle. So here's the graph shown here when we take the plus. When you take the minus, all the y values are negative, so that gives us the bottom half of the circle. Okay, so we have two explicit equations that put together correspond to the original implicit. So if you wanted to find slope of a tangent at a particular point, you'd have to figure out, first of all, which of these two curves is that point on, and then you could find the derivative to give us the slope of the tangent, and you could use our normal derivative rules because these are normal explicit functions. The other option is to leave it in implicit form, and you just have one equation to deal with, and then use the methods we're going to learn in this section for finding derivatives of an implicit equation. So we were just discussing that even if your equation is in implicit form, meaning it's not solved for y, we're going to learn the method of implicit differentiation so we can still find dy dx. Well, some of these implicit equations are actually not functions, as we saw with the last example. The graph of that circle failed the vertical line test, so it's not a function. But it still has tangent lines, and dy dx still represents the slope of a tangent, so we're still interested in being able to find dy dx. So the basic method is you always start here. You differentiate both sides of the equation with respect to your independent variable, which in this case is x, and then you just use algebra to get dy dx by itself. That's the basic overall strategy. There's some details in there that we need to go through, which we'll do as we go through some examples. So in all the examples we do in this section, we're always assuming y is defined implicitly as a function of x and that it's differentiable so that this method will work correctly. We'll go through this example to illustrate how the method of implicit differentiation works. So we're taking the same equation we've been looking at, which represents the circle of radius 5, and first we want to find dy dx, and then we're going to use that to help us find an equation of the tangent to this curve at the point 3, 4, which is a point on the circle. So we'll start by finding dy dx. So remember we said the first step of implicit differentiations is to differentiate both sides of the given equation with respect to the independent variable. Now, because we're trying to find dy dx, right, that means we're assuming y is a function of x, so the independent variable is x. So notice here we've just put d dx of the left side equals d dx of the right side. We still have to compute those two derivatives. On the left, we have the derivative of a sum. So the first thing we do is we use the sum rule. We can split the derivative up to each term in the sum. And then the right side is an easy one because we know the derivative of a constant is 0. So we still have two derivatives to compute, so we'll continue with that. Up at the top, I've copied where we left off on the previous slide. So we have these two derivatives to compute. The first one is very simple, right? Just use the power rule to take the derivative of x squared with respect to x, and we get 2x. The second one is something new that we haven't seen yet, because notice it's asking us to find the derivative of y squared with respect to a different variable x. The inside is a function of y, but we're taking the derivative with respect to x. If that said d dy of y squared, we would just use the power rule and get 2y. It would be very simple. But this is new, so because the variables are mixed here. So keep in mind that y is a function of x. Right? We've assumed that from the beginning because we're trying to find dy dx, so we've been assuming y is some implicitly defined function of x. So imagine that y has some formula, like y could be 3x squared minus 5x plus 2 or something like that. So if you think about it that way, this y squared, if you replace the y with its formula, you would have that expression with x's in it squared. And that's a composite function. Okay, so we're dealing with the derivative of a composite function. Okay, so we're going to say y squared is a composite function where the inside part is y. Remember, y is some function of x, so there's some expression there with x's in it. That's the inside part. The outside part is the y squared. So the outside is a power function, right? The variables in the base, constant power, that's a power function. So we're going to use the chain rule to find this derivative. So looking over here, right, this is just copying this derivative we're trying to find. The chain rule says you take the derivative of the outer function, and that would be with respect to the variable that you see here, y, right, times the derivative of the inner function. Now the inner function is y as a function of x, so that derivative would be dy dx. Now notice this derivative here that we still need to compute. The variables aren't mixed anymore. These are both y's. So it's just a normal type of derivative at this point. So y squared is a power function, use the power rule, bring the 2 down in front, reduce the power by 1, we get 2y. And then the dy dx can just stay as it is. So now, from here, let's substitute in for these two derivatives. So this first one is 2x, written that here, plus this derivative is 2y dy dx, so we put that here. And then the right side we just keep the same as 0. Okay, so just to make it clear, this whole equation, we're substituting into it to get this. So now the rest is just algebra. So we're going to use algebra to do this last part, to solve for dy dx. So solving for dy dx means just add, subtract, multiply, divide until you get this term right here by itself. So those steps aren't shown here, so I'm going to add those in. So first I would take the equation just above and subtract 2x from both sides. So now we have 2y times dy dx equals negative 2x. Then I would divide both sides by 2y, and the left side is now dy dx. The right side is negative 2x over 2y. The 2's cancel and you get negative x over y. And so that takes us down to explains exactly where this came from. So we just completed the first part of this example, which we were asked to find dy dx. So now we'll go on to the second part. Here's the formula we just found for dy dx for this given equation. The next thing we were asked to do was to find an equation for the tangent line at the point 3, 4. So at the bottom I've got a picture of our circle of radius 5, right? So we know I can mark these off at 5. So the point 3, 4 looks like it's around here. And then we could sketch in what the tangent line would look like at that point. That's the line we're trying to find the equation of. So what we need to do is take our dy dx. Remember, we know that this will tell you the slope of the tangent at any point. So you have to plug in the information for your point, which point you're interested in. Now in the past, that meant you only had to plug in the x-coordinate of the point because that automatically determined the y value. But here, notice the formula has on the right, you have an x and a y, so you've got to plug both of the values in from your given point. So we're going to plug in 3 for x and 4 for y into this equation for dy dx, and we get negative 3/4. So that's the slope, right, for this line. To write its equation of any line, you need the slope and a point. Well, the point was given, right? It's the point where it's tangent. So then using the point slope form, you take y minus the y-coordinate of your point, which is 4, equals the slope, negative 3/4, multiplied by x minus the x-coordinate of your point, which is 3. And then if you wanted to simplify this, you could distribute over the parentheses, add the 4 to the right, and solve it for y, or here we've written it in another form. We sometimes write lines constant times x plus constant times y equals a constant. Either way is fine. That's just a simple type of simplification. So now we've completed an example using where we had an implicit equation, and we learned the method for how to find dy dx. And then we saw an application in using that dy dx to find the slope of a tangent. Here's another example where we're given an equation and asked to find y prime. And clearly this is an implicit equation because it's not solved for y. It would also be very difficult to solve it for y because notice there's a y cubed in one term and there's a y in another term. So rather than even attempting to solve this for y, we're just going to use implicit differentiation. So if you remember, the first step is to take the derivative with respect to x on both sides. Because we have a sum and difference on the two sides, I'm going to go ahead and split it up to the individual terms. So we have the derivative of our first term on the left minus the derivative of the second term, and make sure you're putting dx for these, right? Because we're asked to find y prime, which implies y is a function of the other variable, in this case x. And on the right, we have ddx of the first term plus ddx of the second term. So with implicit differentiation, it helps to do this because you want to make sure you're paying attention to which variable is which in each case. Now back to our first term, this derivative here, notice this is a product. It doesn't look like a product of functions of x, right? If you had a constant times x squared, you don't have to use the product rule there. You only need the product rule if you have a function of x times a function of x. And it doesn't really look like we have that because we have a function of x times a function of y. But remember, we're viewing y as a function of x. Right? When we say y prime, that automatically means we're viewing y as a function of x. So even though we don't see any x's here, y really has some formula that's made up of x's. So this is a product, and we're going to have to use the product rule on this one. Okay, so let's go ahead and do that. So product rule says first times derivative of the second plus second times derivative of the first. So we still have some derivatives to do, but we'll do that on the next step. For now, let's continue to the right. So we have minus d dx of 3y. This is one of those cases of mixed variables. So you have to use the method we learned in the last example, where you view this as a composite function. The outer function is 3y. The inner function is, remember, y is actually a function of x. So we start with the derivative of the outer function, and that's where you just apply the normal, you pretend like you're taking the derivative here with respect to y instead of x. And so the derivative of 3 times the variable is just the constant 3, because the derivative of y with respect to y is 1. So the derivative of 3y is 3. There's this minus in front of the whole thing. And now you need the derivative of the inside part. With implicit differentiation, the inside part is always y is a function of x. So that derivative is always dy dx, unless you're using different variable names. But it's never anything more complicated than d of your dependent variable over d of your independent variable. Okay, so that finishes this term. The right side is easy because notice here, no mixed variables. So just apply normal rules to take the derivative of 5x with respect to x, and that's 5. And then the derivative of 1, since 1 is a constant, its derivative is 0. We still have 2 derivatives left to do. Okay, so on the next one, we'll just keep this x squared, but this derivative's got mixed variables. So again, we have to use the chain rule on that. Okay, so the inner function on these, it's always the same. So here y is a function of x, that's our inner function. The outer is y cubed. So the normal, that's a power function, so if we were taking the derivative with respect to y, you'd get 3y squared. Okay, so let's start writing this. We keep the x squared. The derivative of y cubed with respect to y is 3y squared. And then we need the derivative of the inside part, which is just dy dx, right? Because again, the inside part is just y as a function of x. Okay, so that finishes this derivative. So now we continue on, plus y cubed. Now the next derivative does not have mixed variables, right? It's just derivative of x squared with respect to x, so just use the power rule, we get 2x. And then I'm just going to copy the rest. So now we've done all the derivatives. The rest is algebra. So now we're going to use algebra to solve for dy dx. Okay. Now there are 2 terms that have dy dx in them. So we want to, in general, you want all the terms that have dy dx on the left and move everything else to the right. So I'm going to keep this first term on the left, 3x squared y squared dy dx, and then I'm going to keep the minus 3 dy dx on the left. I want everything else on the right. So I already have 5 on the right, but then I need to move this term over to the right. So I'm going to subtract 2xy cubed from both sides. Once you've done this, where you've gotten all the terms with dy dx on the left, because every term on the left has that same dy dx, you can factor it out. So that combines multiple appearances of dy dx into one appearance by factoring it out. So in the first term, after you factor that out, we're left with 3x squared y squared. And on the second term, we're left with minus 3. Right side is still the same. Now we're almost there. One more step. To get dy dx by itself, we just need to get rid of this, and we do that by dividing both sides by that entire expression in parentheses. So let's fit that up here. Now we have, on the left, we'll just have dy dx. On the right, here's what we already had. That'll be our numerator. And then we're dividing the entire right side by the expression in parentheses. And we have it. Okay, so now we've seen two examples. Hopefully you're getting a feel for it. We had to use some extra rules this time. Right here we needed a product rule. And then we had two instances where we had derivatives with mixed variables. One was here. And the idea is first just take the derivative with respect to y. That gave us the 3. And then you always have to multiply by this extra factor dy dx, and that again is from the chain rule. It's the derivative of the inside part. And then we had another derivative here that had mixed variables. So first just take the derivative here with respect to y, which is 3y squared, and then multiply by dy dx, right? That extra derivative of the inside part is always just dy dx. Here we have another implicitly defined function, clearly not solved for y and would be probably impossible to solve for y because one y is inside of a cosine and the other y is in an exponent. So to find dy dx, we're going to use implicit differentiation. So first step, as always, take the derivative with respect to x of both sides. So here's derivative of the left equals derivative of the right. Let's start on the left. This is a composite function because instead of just cosine x, we have cosine of some other expression. So we need the chain rule. So we always start with the derivative of the outer function. The outer function is the cosine function, and its derivative is negative sine. But you need to keep the inside part, right? It's not negative sine of x, it's negative sine of the same input. Now we multiply by the derivative of the inside part. Now this one is a little more complicated, so I'm just going to write that before we actually take it. I'm going to write derivative of exactly what we're taking the derivative of. So we'll complete that in the next step. So that finishes this stage for this term on the left. On the right, notice this derivative is mixed variables. So we have to use the chain rule technically for this. So you start with what you see is the derivative of e to the 2y, but we're going to take the derivative with respect to y. That's a chain rule problem. The inside function is 2y, the outside function is e to the x, or e to the u, right? So the derivative of the outside, the exponential function, e to a power, is itself. So here's itself. Now the derivative of the inside part, let's just write that out. Of course, that's with respect to x, right? Because all of our derivatives here are with respect to x. And the inside part is 2y. Okay, so that completes that step. Now in the next step we have two derivatives to do. So we keep this first term as it is. Now this next derivative is over a sum, so we can go one term at a time. So starting with the 2x, derivative of 2x with respect to x, that's not mixed variables, so it's just a normal derivative. So that would be 2 plus, now the next one is 3y, and we're taking the derivative with respect to x, so that's mixed variables. So the outer function is 3y, so you start by taking that derivative with respect to y, which would be 3, but then you have to multiply by the derivative of the inside part. The inside part is y as a function of x, so that derivative is just dy dx. So that completes the derivative there. Now on the right, we keep the e to the 2y. This derivative is mixed variables. The outer function is 2y, so first just take that derivative with respect to y, and that would be 2. And then multiply by the derivative of the inside part, which, just like before, that's dy dx. So now that we've done all the derivatives, the rest is algebra. So we want to take this equation and solve for dy dx. Okay, so just like we did in the last example, we want to get all the terms that have dy dx on the left and everything else on the right. Now notice here it's a dy dx. And we have one over here, but this one on the left is a little problematic because this term, the plus 2, doesn't have it. So we have to separate out this plus 2. So what we're actually going to need to do is distribute this over the parentheses, and then the first term won't have a dy dx, so we'll eventually move it to the right. Okay, so let's go ahead and distribute. Negative 2 sine of 2x plus 3y, and then distribute that sine term to the second term. We'll get minus 3 sine 2x plus 3y multiplied by dy dx. And we'll just keep the right side essentially the same, 2e to the 2y dy dx. Now you can see I'm going to underline the two terms that contain dy dx. So I want to get those two terms on the left and everything else on the right. And I think we're going to need to go to a new slide to finish this one. Here I've copied where we left off. So we were just discussing the two terms that I underlined are the terms that have a dy dx. So we want to get those two terms on the left. So I'm going to keep the one that's already on the left, and then to move that term on the right, I need to, over to the left, I need to subtract it from both sides. So minus 2e to the 2y dy dx. Now we still have to handle this term. Since it doesn't have a dy dx, we want to move it to the right by adding this expression to both sides. So on the right, we'll have positive 2 times this sine term. Now on the left, both terms have dy dx, so we can factor it out. Right? That's how we combine two dy dx terms into one. So in the first factor, we're left with negative 3 times the sine term. And on the second term, we're left with minus 2 e to the 2y. On the right side, still the same. And one more step to get us there. To get dy dx by itself, we need to divide both sides by this entire expression in the brackets. And if you wanted to, you don't have to do this. Notice both of these terms are negative, so you could pull the negative out front. And then when you divide over, that negative would also get divided over. And then both of those would be positive if you do that. So on the right, this is what we currently have. It will be our numerator. I'm dividing by what's in the brackets, but I'm going to make them both positive. And then I'm also, right, because I made those both positive, it means I factored out a negative, so I'm technically dividing by a negative, but it probably looks better just to put the negative either in the numerator or out in front of the fraction. I'll just put it here because that's where I have space for it. Okay, so we made it. We got to our dy dx. So in these three examples, we've seen a lot of the situations you'll encounter when you're doing implicit differentiation, including using the product rule, the chain rule, and a lot of the other differentiation rules we've already learned, right? So we're still using the rules we learned before, but not in a direct way, right? It's part of this method. We're using them within this new method we're learning of implicit differentiation. In this example, we're asked to find a second derivative, y double prime, and then the equation we're given is implicit, right? This is not solved for y. So to find a second derivative, it's the same idea that we've seen before. First you have to find y prime, get a formula for that, and then take the derivative of the formula for y prime, and that will give you y double prime. The only difference is we're going to be using the implicit differentiation method to find first y prime and then y double prime. So here we start with, to find y prime, we would take the derivative of both sides of the given equation with respect to x. Right, so if we wanted to write out that step, we would say derivative of the left side, and because there's a sum, you could split it up to both terms, equals derivative of the right side. All these derivatives are with respect to x. Now this first derivative is, both variables are x, they're not mixed, so it's just a simple derivative 4x cubed using the power rule. So we write that. The next derivative, we have mixed variables. So we start by taking this derivative with respect to y, which would be 4y cubed, and then you multiply by dy dx, which is here. So we've used the notation y prime instead of dy dx. And the right side, the derivative of a constant is 0. So now we use algebra to solve for y prime. So there's only one term with y prime. So to get it by itself, we would start by subtracting the 4x cubed from both sides, and that would give us, on the left, we have 4y cubed y prime. On the right, we have negative 4x cubed. And then to finish getting y prime by itself, we would divide both sides by 4y cubed. Notice the 4's cancel, and we would end up with negative x cubed over y cubed. So there we've arrived at our formula for y prime. So on the next slide, we'll start the process of finding y double prime by taking that formula we just found for y prime and computing its derivative with respect to x. This is the formula we just found for y prime. So like I said, the next step is to find y double prime by taking the derivative of this formula with respect to x. And so here we've written y double prime is the derivative with respect to x of this formula. That's the formula for y prime. Notice this function here is not solved for y, right? If it were solved for y, it would only have x's on the right. We don't have that, so we're going to have to use implicit differentiation for this derivative also. So we do have a quotient here, and it's the top and bottom are both functions of x, right? Because we've assumed from the beginning here that y is a function of x. So using the quotient rule, first just carry along the negative sign, and then quotient rule here we would take bottom, which is y cubed, times derivative of the top, so we've notated that here, minus top, there's the x minus x cubed, times derivative of the bottom, so derivative of y cubed. So all the derivatives you write here need to be with respect to x. And then the bottom, you take the original denominator and square it. So now we have two derivatives to do. So we keep the minus, and then in the numerator we keep this y cubed. This derivative is not mixed variables, so simple, it's 3x squared using the power rule. The next term, keep the minus x cubed. Now this derivative is mixed variables. So first we take the derivative with respect to y, so that's 3y squared. And then we have to multiply by dy dx, which you could also call y prime. So there's that. Bottom, in this situation, we multiply exponents, so that's y to the 6th. Okay, so now we're not going to stop here because if you look at what we have, there's a y prime in it. So we don't want to express y double prime in terms of another derivative. we want to have no primes on the right. So we need to substitute in for y prime, and where we can use that is, this says equation 3, but that's referring to the equation up above at the top for y prime. I'll just copy that here. Negative x cubed over y cubed can replace y prime. So on the next simplification, we're going to copy this exactly, but we're going to replace this y prime right here. So here, I guess we didn't copy exactly. We made it look a little nicer. So 3x squared y cubed. Keep the minus sign out in front, by the way. And then here, minus 3x cubed y squared, and then we make the substitution right here. And we keep the denominator the same. So technically we're done, right? We have our formula here for y double prime, but on the next slide we'll do just a little more simplification to make it look better. So here's where we left off. I'm going to do a little simplification, and the first step is just going to be on the second term in the numerator. So I'm keeping the first term in the numerator the same. Now the second term I have minus times minus is plus, and then I have this 3, then I have x cubed times x cubed. So in that situation we add the exponents, so that's x to the 6th. And then I've got y squared over y cubed. So 2 of those factors cancel, and I'm left with 1 factor of y in the denominator. Now the only thing that's not so nice here is having this fraction within the numerator. So we could clear that fraction out by multiplying top and bottom here by y, right? Because when we multiply this term by y, it'll cancel out that y on its denominator. So I'm going to multiply by y over y, which we can always do because we're just multiplying by 1. So in the numerator, let's keep this negative sign. I'm going to distribute this y to both terms. So on the first term, I'll have 3x squared y to the 4th, and then I'll have plus, and on the second term, the y's will just cancel. So the second term is just plus 3x to the 6th. Denominator, I'm multiplying y to the 6th by y, so add the exponents, that becomes y to the 7th. So it would be perfectly fine to stop here. This could be our final formula for y double prime. This is an example from the book, and they actually go further, and they use kind of a clever trick that is not obvious at all that you could do this, but I'll just show you because it's kind of interesting. So next, I'm only going to simplify here in the numerator. So notice both terms have a 3, that could be factored out. And then both terms have an x squared that could be factored out. So in the first term, that leaves y to the 4th, and in the second term, it leaves x to the 4th, right? Because we pulled out 2 factors. Now here's where they're clever. That expression in parentheses is seen in the original equation. In this example, the original equation that we were given was x to the 4th plus y to the 4th equals 16. And notice this expression in parentheses is the same as the x to the 4th plus y to the 4th. So we know that could be replaced with 16. Okay, so making that substitution, we have negative 3x squared times 16 over y to the 7th. And then the final simplification, we'll say y double prime equals negative. So in the numerator, 3 times 16 is 48. So we have 48 x squared over y to the 7th. So it was just kind of lucky that we were able to make that substitution in the parentheses by using the original equation. So I wouldn't expect that you do that on a test. It's just you could have stopped earlier in the simplification process. We're going to learn some more derivative formulas in this section. So we'll be learning how to take the derivatives of logarithmic functions and the inverse trig functions. And we're doing these now because deriving these formulas involves using implicit differentiation, which is what we just learned in the previous section. Here I've presented the formulas for the derivative of a logarithmic function. So here on the left, we have the formula for the derivative of log of any base b of x is 1 over, and then the denominator is x times natural log of b. Now to the right of that is the special case, right? We're all familiar that the natural log is the log with base e. And so notice if you use the first formula for the derivative of log base e of x, over on the right, we'll have natural log of e for this factor, which we know is equal to 1. And so the denominator is just x, so you get 1 over x, which we have here. So the second one is not really a new formula, it's just a special case of the first one. So we really just need to derive the first one. So to derive that, I'm going to start by letting y equal the function we're trying to find the derivative of. So this is equivalent to an exponential equation. If you remember from pre-calculus, one way to get the equivalent exponential equation is to start with your base of your log and then come over around here and say to the power of what's over here equals whatever's inside the log. So in this case that would say b to the power y equals x. Now we're going to use implicit differentiation on the equation I just wrote. Okay, so we take the derivative with respect to x on both sides. So we have the derivative with respect to x of the left side equals derivative with respect to x of the right side. Now look at the derivative on the left. This has the mixed variables, right? We're taking derivative with respect to x, but we're dealing with a function of y. So that's what we just learned in the previous section. The way we handle that is first you take the derivative with respect to y. So because the y is in the exponent, that's an exponential equation. And we already learned the formula for the derivative of an exponential equation is itself times natural log of the base. In this case, the base is b. Now that's just part of the chain rule. Right, so the chain rule says first you take derivative of the outer function. So here we took that derivative with respect to y. Then you multiply by the derivative of the inside part. And as you remember, the inside part is y as a function of x. So the derivative of the inside part would be written dy dx. That finishes the derivative on the left, and then the right is easy because it's not mixed variables. So the derivative of x with respect to x is 1. And then the next step is always to use algebra to solve for dy dx. So in this case, we just need to divide both sides by b to the y natural log b. So on the right we'll have 1 in the numerator, and then we divide by b to the y times natural log of b. But notice up here, b to the y is equal to x, so we can replace this b to the y with x. We get 1 over x natural log b, and now we've derived the formula, right? Because we started by letting y equal this log b of x. And so dy dx represents the derivative of this log base b of x. And we showed that it's equal to this expression, which is what we had in our formula up here. We'll do some practice with these formulas in this example. So first we have f of x equals log x. So you may remember from pre-calculus, if you see a log with no subscript, that means the base is 10. So now we have f prime of x equals, so our formula, remember, was 1 over x times natural log of the base, and this one had base 10. Okay, so maybe I should write that up here just to remind us of the formula. Derivative of log base b of x equals 1 over x natural log b. That was the formula we presented on the previous slide, and we're using that here. Okay, let's go to the second one. So this one, we can see the base is 2, but notice instead of just having an x plugged into the log function, it's a more complicated expression. That means this is a composite function, so we need to use the chain rule. Okay, so, sorry, that's a little hard to read. So for g prime of x, first let's identify the inner and outer functions. So the inner function is what's in the parentheses, which means the outer function is just log base 2 of the inner function, or so think of it as the log base 2 function. So we start with the derivative of the outer function, the log base 2 function. So we just said that is 1 over x, but here, remember, you don't just use plain x when you're using the chain rule for the derivative of the outer function. Instead of x, you use whatever is in place of where x usually goes, which in this case is the expression in the parentheses, the inner function. So it's 1 over x times natural log of the base, which is, this one has base 2. Okay, so that was applying this rule to log base 2 of the inner function. So it's basically just in place of the x, we have this inside part. Now the chain rule has the second factor, which is the derivative of the inside part. So we need the derivative of the part in parentheses, which would be 6x plus 4. Now it might make it look a little better if we put that in the numerator. So 6x plus 4. And then we're done. Okay, let's go to the third one. So here we have a quotient. The natural log of x is part of that quotient, but the bigger picture is we have a quotient. So we need to start with the quotient rule. Okay, so h prime of x equals a fraction. The denominator part's the easiest. Just take the old denominator and square it. Now in the numerator, we start with bottom times derivative of the top. So the derivative of natural log x. So we discussed earlier, natural log means the base is e. So in this formula, you would have 1 over, and then down here we have x natural log e, but natural log e is 1. This is actually the special case we saw. The derivative is just 1 over x. And natural log is the type of log we see more than any other. And so we usually just remember the shorter version. The derivative of natural log x is 1 over x. Okay, so back to our quotient rule. we just did bottom times derivative of the top. Now we need to do minus top times derivative of the bottom. So top is natural log x, and then derivative of the bottom, 3x squared minus 2. And then you could do some simplification, but I guess if we did anything here, I might multiply top and bottom by x, because that would clear out this fraction within the numerator. Okay, so if we did that, times x over x, in the numerator, we would have, on the first term, the x from here would just cancel that, so we're just left with what's in the parentheses there. And then in the second factor, you just have to multiply by x. So you could distribute this x over this parentheses, so 3x cubed minus 2x times the natural log. And then in the denominator, we're also multiplying by x, so just put in that extra factor. So x times what was already there. And I think that's a pretty good simplification, so we'll call that our h prime. So we just had a little time to get started on this section. We've learned the derivative of logarithmic functions, and we still have some more derivative formulas to learn, which we'll do next time. So let's summarize now what we covered today. We covered parts of 3 sections. We started by finishing where we had left off in section 3.4 on the chain rule, and mostly we just did more practice. We did several examples where we used the chain rule to compute derivatives of composite functions. And then we derived a formula for the derivative of exponential functions. And we did that here because this derivation used the chain rule. So we had already learned the derivative formula for e to the x. What we derived here was a formula for any base b to the x. Then we did all of section 3.5 on implicit differentiation. So we learned a method here for the situation where you have an equation that's not solved for y. That means it's an implicit equation. And we learned a method where we could still find y prime. And then we just started section 3.6, where we're learning more derivative formulas, this time for logarithmic functions and inverse trig functions. And so far, we derived the formulas for derivatives of logarithmic functions. So we'll continue with this section next time.